All right. Hi again, Holly. I'm sorry. Hi. Whew, I'm getting tired. Hi again, Trisha. Sorry. I'm just here finishing up your review of exam two and providing you the feedback I wanted to provide you here. So I've gotten down to the problems that were unattempted at this point. So going back, question four, we are talking about this type of problem where you're given the position of a body moving along an s-axis is given by this position function. So in part A, we want to find the acceleration each time the velocity is zero. So velocity, first of all, find the velocity. Velocity is the derivative of position. So you take the derivative of this guy. Now I need to know when the velocity is zero, so I need to factor this. If possible, I can factor out a 3 first and foremost, and then I can factor the quadratic that's left, and I see that the velocity is zero at t equals 4 and t equals 6. And then I can find acceleration, which is the derivative of velocity, and then plug in and simplify it. Makes it easy to plug in the number, 6 times the quantity t minus 5. So then I want to know what's the acceleration at those 2 times of t where the velocity was 0 at 4 and 6, and I get minus 6 and 6. Now what's the speed? So speed is the absolute value of velocity, the magnitude of velocity. So it wants to know the speed when each time the acceleration is 0. So we already have acceleration set that equals 0. That happens at t equals 5. So the speed when t equals 5 is the magnitude or the absolute value of v of 5, the velocity of 5. So you plug in 5 into the velocity function. It's easiest to plug in when I factored it here. So 3 times 1 times minus 1 minus 3, but the absolute value is 3. So there's your speed. And see what's the total distance traveled. So basically for the total distance traveled, I have to understand I want the distance traveled between 0 and 4. So the particle's moving in one direction from, 0 to 5. The particle's moving in one direction from 0 to 4, and then at time 4 it stops. So it could go back in the other direction. I didn't analyze to see which direction it went, but it stopped at time 4, and so then from 4 to 5 it's going in either the same direction or a different direction. So, but safest thing is to break it up at 4. So if I want the distance traveled, I want the absolute value of s of 4 minus s of 0 plus the absolute value of s of 5 minus s of 4. So if you work that out, you get 114. Problem 5. Problem 5 is a similar problem where you throw a rock upward vertically from the surface of the moon. It has this position function, okay, which is in meters. All right. So find the rock's velocity and acceleration. That just means velocity is a derivative of position and acceleration is a derivative of velocity. So those are easy derivatives. Part B, how long does it take to reach its highest point? Well, when it reaches its highest point, the velocity is equal to 0. So we're going to set the velocity equal to 0. And we see that happens when t is 15 seconds. Part C, how high does the rock go? Well, that just means it reaches its highest point at 15 seconds. So what's its position at 15 seconds? You just plug in 15 to the position function, get 180 meters. Part D, it says how long does it take the rock to reach half its maximum height? So that means we want to know at what time is its position half of its maximum height, which is max height is 180, so half is 90. So you set 90 equal to the position function and solve for t. So this just becomes a quadratic equation. So using the quadratic equation, you get these 2 times. That's because on the way up, it passes 90 meters, and then on the way down, it passes 90 meters again. Okay? And then in part E, how long is the rock aloft? Well, the easiest answer is to just double what you got in part B, because if it takes 15 seconds to go up, it's going to take 15 seconds to come down. Or you could do it as, hey, I know that when the rock hits the surface of the moon again, its position is 0. So let's set the position equal to 0 and solve for t. That gives us 2 times. So t is either equal to 0 or 30. Well, t is 0, that's when you first throw it up, and then t is 30 when it hits the ground again. So 2 ways to think about E. Question 8. So r is 2 minus theta squared sine theta. So if you want the derivative of r, the derivative of this function with respect to theta, that means your theta is your variable now. So the derivative of 2, a constant, is 0. And the derivative of minus theta squared sine theta is a function times function. You got to use a product rule. So first times the derivative of the second, plus the second times the derivative of the first. Simplify it. All right. Problem 12. next one. No, problem 12, you hadn't attempted or showed me the work. Oh, on A and B. But on parts E through H, C through H, sorry, you didn't get those correct, and I worked them all out for you. So for example, the derivative of F times G, you got to use product rule. So it's first times derivative of the second plus second times derivative of the first. Plug in those numbers from X equals 3 on the table. You got it. Chain rule for these last, quotient rule for D, F divided by G, so quotient rule. Chain rule for the square root of f of x, so you write as f of x to the 1/2, so the derivative of that is 1/2 times f of x to minus 1/2, then multiply that times derivative of the inside, f prime. And then these are both chain rules as well. So make sure you look at these and make sure you understand these, okay? How to do these. Ask if you don't understand. 13. So this one we have to use implicit differentiation. We need to find dy dx, but we can't set this as y equals some function of x and use our typical rules, so we have to use implicit differentiation. So you take the derivative with respect to x of the entire equation. So x to the fourth is easy, that's 4x cubed. But then cosine of y, well, y is an unknown function of x, so this is a chain rule. First of all, you take the derivative of the cosine, which is minus sine of the inside y, then times the derivative of the inside dy dx. And then x cubed y to the fifth, on the right side, you got to use the product rule. So first times the derivative of the second. Well, x cubed, and then the derivative of y to the fifth would be 5y to the fourth for the derivative of the outside, but then multiply it times the derivative of y, so dy dx. And then derivative of the first times the second gives you that. So then it just becomes an algebraic equation to solve for dy dx as a variable. So put everything with dy dx in on the left side and everything without dy dx on the right side. Factor out the dy dx and then divide by that term and you have your answer. 14 is similar, an implicit differentiation, but they want you to get two derivatives, the first derivative and the second derivative. So the first derivative, you take the respect to x of both sides. So that means 6/7 x to the minus 1/7, right? Power rule. Well, now this one I have to use a chain rule because I don't know what y is as a function of x. So it's 6/7 y to the minus 1/7 and then times dy dx equals the derivative of 155, which is 0. So that I can solve easily for dy dx. And I get dy dx is this guy. So what I'm doing is I'm flipping the x and the y so I can write to the power of 1/7 instead of minus 1/7. Okay, so there's my first derivative. How do I get the second derivative? I take the derivative of the first derivative. This needs a chain rule. So it's minus 1/7 y over x to the minus 6/7 times the derivative of the inside, which is a quotient rule. Low d high, so x dy dx minus high y d low is 1 divided by x squared. Take the dy dx, substitute it in for dy dx, and then just do algebra to get the exponents simplified as much as possible. 15 is another implicit differentiation because we need to find the slope of a curve where we can't get y equals f of x, so we have to do implicit and solve for dy dx. So I take the derivative with respect to x of the entire equation. So again, I don't know what y is as a function of x, so this is a chain rule. So it's 40y to the fourth times dy dx. Derivative of 5x to the fifth is just 25x to the fourth. Derivative of 9y is 9 times, I don't know what y is, so I can just write dy dx. And the derivative of 4x is 4. So then I just solve for dy dx. That's pretty basic algebra there to solve for dy dx. And then I plug in at the point 1, 1, and I get negative 21 over 31. 18 is a related rates problem. All right, so in 18, you're told the diameter of a tree is 14 inches. You're told the following year the circumference increased 1 inch. That means dc dt over the year is 1 inch. And how much did the tree's diameter increase? In other words, we want dd dt. So I need a relationship between circumference and diameter. So we know that circumference is 2 pi r, but r, or 2r, is the diameter. So circumference is also pi d. So now I can take the derivative with respect to t of both sides of this equation. dc dt equals pi times dd dt. So they want dd dt, so solving for dd dt, it's 1 over pi times dc dt. They told you that dc dt was 1. Plug that in, so your answer is 1 over pi, which, plug it in a calculator, is about 0.3183 inches. They also want to know how the area changes. Well, area is pi r squared. So r is, well, 2r is d, so r is d over 2. So d over 2 squared. In other words, it's pi over 4 times d squared. So you take the derivative of both sides of that with respect to t. dA dt is pi over 2 d times dd dt. So power rule, bring the 2 down, and then multiply the derivative inside dd dt. So then you just plug in these values, right? Pi over 2, the diameter was 14 inches, and we found dd dt to be 1 over pi. The pi's cancel, so 14 over 2 is 7. All right, so then 25. Here you're given the first derivative of a function and asked to find the critical points in part A. So we know that the derivative tells us critical points. You set it equal to 0, so that happens when the numerator is equal to 0. When x equals 5, that's a critical point. But also, we have critical points where the derivative doesn't exist. So notice that if you plugged in x equals 0 here, you'd be dividing by 0. So that's also a point, a critical point. So we have two critical points, 0 and 5. And then you just have to apply the first derivative test. So the way I like to apply a first derivative test is draw a number line, x, and then value of f prime of x above it. So plug in your critical points, 0 and 5. I say, hey, the derivative doesn't exist at 0. It's 0 at 5. And then in between critical points, you got to figure out what's going on. So I check the derivative at -1. I see that it's positive. So that means the function is increasing. From minus infinity to 0, the function is increasing. I check the derivative at 1 between 0 and 5. I get the derivative is negative. So that means the function is, the derivative is negative, which means the function is decreasing. So that means we have a local max here. And then I check the derivative beyond 5. So at 6, I get 1 over 6 to the 1/5. So in other words, that's positive. So again, the function is increasing. So I have a local min here. And so you know the intervals of increase and decrease, and you know the local max and the local min. 27. Okay, here they give us f of x equals sine of 7x on the interval 0 to 2 pi over 7. So we know that sine of x is 2 pi periodic. Every 2 pi, it repeats that sine wave. Well, 7 over x would be 2 pi over 7 periodic. So from 0 to 2 pi over 7, we cover the whole sine of 7x function. So this is half of 2 pi over 7, which is pi over 7. Half of that's pi over 14. And then in between that's 3 pi over 14. So you can see there's local minimums at 0 and at 3 pi over 14. And then there's local maximums at pi over 14 and 2 pi over 7. This is an absolute max, and this is an absolute min. And then you can take the derivative, which is 7 cosine of 7x. So it's going to look like the cosine function, just have a magnitude, just have an amplitude of 7 instead of 1. Okay, and then 30. So 30, we want to graph this rational function. The easiest thing to do is we have a rational function. We want to figure out where there's holes and where there's asymptotes first. So you factor the denominator and you factor the numerator, and you can say, oh, look at the x plus 2 factors cancel. That means that at x equals -2, there's a hole in the graph. The x minus 2 in the denominator cannot cancel with anything in the numerator, so that's an asymptote at x equals 2. Okay, so you look over here to see if there's any graphs that have a hole at x equals -2, and both A and B do, but only A shows that there's an asymptote at x equals 2. So A is the correct answer. Okay, so Trisha, that's your feedback on exam 2. If you have any questions, please don't hesitate to reach out, and good luck finishing up the course.